Hello everyone, can you hear me? Perfect. Welcome to our event on the topic of Rust, a programming language that is very unique and that we will all find out about what makes it unique, why it's so interesting and where it is used in practice in those 3 talks today. But before we dive right into Rust, I want to give you a quick introduction to who is organizing this event, which is 0xA. It's actually funny that we're doing a Rust event again, because this was actually the very first event we had, which was just a mini talk by Matthias, where we were getting together as like 5 to 10 people in some room at university, which is now a little bit bigger room at university, and we're doing bigger events now. So, who are we? We are a collective of students, of tech enthusiasts, of mathematicians, and so on. And our idea is to bring people together, to learn together, to share knowledge, and this is like our mission. This is what we want to do, to build a community around this. And what do we do actually? How do we achieve this? First of all, of course, by events, like this one today. You will see 3 talks, and each of the talks will have like a different viewpoint on the topic today. So this is Rust, so we will see something from the industry, and usually we also have professors here who talk about what it is from a research perspective. But we also want to see what students, for example, think about a topic. So we always try to get different viewpoints on one topic together and tend to discuss it. But theory is not enough, so we also do workshops where we learn hands-on how to do something. And something that was very cool, that was our quantum computing workshop a few months ago, where we had an IBM expert here in Linz who taught us how to basically program a quantum computer right now. And doing that hands-on yourself is a really cool experience. It doesn't end here. We want to build a community. And how do we build community? To get together, to have fun, to play games, to do stuff. This we do by our chit-chats, which are usually bi-weekly, where we just get together, have some fun, have some snacks, some drinks, play some games, and build a community around our mission. What you will see after this event today is networking. And of course, we have networking with food and drinks that are for free, of course. We want you to, after you get all the inputs, to be able to discuss them with your peers, to maybe find new friends, maybe to have new ideas for projects and so on, and to have just a chill end at the end of the presentations. But all of this is not possible without you, people who do this, people who help us organize the events, who help us do our marketing, our social media, and so on. So if you're interested in making pictures, doing videography, maybe cutting stuff and doing social media things, we're always looking for people who help us with that, who want to be part of 0xA. So if you're interested, just talk to us after the event, scan the QR code or get in touch with us. We really want to have like a big collective of many people who do the same so we can achieve our mission. And all of this would not be possible without our partners, of course. So we are partnered with 5 Square, who are a company who actually originated here at the OIC. They're now next to the JKU campus, and they're doing all sorts of stuff in the technical domain, starting from cloud computing up to AI. They have their own large language model, Kali, right now. They are also trying to predict epilepsy, so they're doing a project in that regard. So they have a lot of fun stuff, and if you're interested, check them out. And also big thank you to the OIC, of course, for giving us this amazing venue here and making it possible for us to have this event here. The OIC, the OIC is the point basically where university meets industry. So here are a lot of labs, but also a lot of companies. So this is a really cool space where ideas get together and new ideas are forged. And with that, I would go right into the agenda. So we start off with an introduction to Rust. So everyone gets on board with us by Stropek. Then we will hear about Rust in industry by Carrara. And at the end, Rust in security. How do those 2 things go together by Matthias Heiden. And afterwards, of course, some networking. And now, let's start with the first talk by Stropek.
1, 2, 1, 2, kann man mich hören? Okay, very good. So let's switch to English. Hello, thank you for having me today talk about Rust. My name is Stropek. I'm a passionate coder and I was invited to introduce you to Rust. And I don't know what about you, but I love to see code. I love to write code. So I decided not to have any slides, but do some live coding. How does that sound? Is that okay? If you would like to talk to me, don't worry, I'm not sick. I'm wearing a mask because I'm very conscious. In my family, I have high-risk patients, and therefore I try to stay healthy. So I'm not sick, so you can talk with me. Everything's fine, but thank you for your understanding. Good, so let's get started. The first thing that I would like to do is I would like to create a project. And that's really nice because we have a tool in Rust which is called Cargo. And with Cargo, I can easily create a new project. Let's call it Why I Love Rust. That's the first thing that you can take away. Cargo is awesome when it comes to project management. No copying files, no npm install, whatever, and having node modules, folders everywhere. You don't need that. You simply have Cargo. And with Cargo, you can manage your entire project. Do you want to run your project? It's simple. Cargo go, Cargo run. Do you want to build your project? Cargo build. Absolutely build. Absolutely no problem. Do you want to add some dependencies? And I hope it's fine for you if I copy in one line here, this one. Do you want to add dependencies? Again, absolutely no problem. You simply say cargo add, and then you add the so-called crate that you would like to add. I mean, if you come from Java, if you come from C#, if you come from Node, you probably think, okay, package management, I mean, what's the deal? But if you come from C, or if you come from C++, that's a really big thing. And with Rust, you can do embedded development, you can do unsafe development, and you can do unsafe development with a microcontroller with the package manager. How cool is that? Good. So, you see, Cargo, that's the first thing that I really, really love. So let's open this up. I'm going to use, oops, that's the wrong one. That's the right one. I'm going to use a development environment that you probably know and love. It's called Cursor. Cursor AI, it's a fork from Visual Studio Code. And what we are going to do today is we are going to read a CSV file. And by reading this CSV file into memory and doing some calculations on top of it, we are going to learn something about Rust. So it's really not difficult. Let me zoom in for you. So as you can see, this is our super complicated CSV file. Not too complicated. I think we should be able to do that. Now, in order for you not to see me doing a lot of mistyping here, I'm going to add at the beginning a bunch of use statements. Now, these use statements that you see here simply import certain types into our program so I can use them in my program. Don't worry about it. If we would have time for many, many hours, I will talk about every single use, but for now, should be fine like that. So let's get started and let's import this file that, you have seen a minute ago. So let's do that and let's create a simple folder, a simple function, read file content. Let's say the file name is a string and let's return here a string, something like this. We simply want to import, let me smart this, is that still fine to read? That is what a function is all about in Rust. Let's zoom in a little bit. As you can see, fn, it's pretty simple to understand. Read file content, you use snake casing. This is a so-called borrow. We are borrowing a string, so we are not taking ownership. We are not responsible for freeing the string. We are just borrowing the string for a certain amount of time. In this case, we are borrowing the string for the runtime of this function, and then we are returning it to the caller, and the caller is still responsible for freeing this string. So ownership is very clearly defined in Rust. You either borrow something, then you don't take ownership, and you don't free the memory, or you take ownership, and then you are responsible for freeing the memory. Okay? This is what we do. And this is the syntax for returning something. I'm returning an uppercase string, and an uppercase string is simply a string which is mutable. Okay? So let's go for it. The first thing that we need is to open the file. Okay, I have AI, so therefore I don't need to write so much code. The rest is, I think, pretty fine. Let's just press tab and let's take a look at the code that you see exactly here. Here you see a file open method. I will zoom in so it's a little bit easier to read. Nothing special. We are passing in the file name, but this one is again very important. Trust me, Rust doesn't have exceptions and you are fine with it. There are no exceptions in Rust. No throw, no catch, no finally, nothing like this. Error handling is way cooler in Rust. And the simplest way of doing error handling is simply to panic if an error happens. Panicking means that you are saying, okay, it doesn't make any sense to continue any further. You do that if you spin up a web API and you are working with the database server in the background and the database server cannot be reached. I mean, what's the point of starting the API? The database server is there, panic. Okay? Panicking is not a good idea if you're doing microcontroller programming, because who should handle the panic? There is nobody there except you. So panicking in a microcontroller world, it's a little bit different, not our topic today. But for this task, we simply say, if there is an exception, please return this panic. If you even want to make it shorter, we can say unwrap. That simply means panic with whatever message comes back from this file.open. So this is a very simple function. Now you know a little bit about borrowing, you know a little about functions. The only thing that I didn't mention explicitly is this beautiful guy here. In Rust, variables are by default immutable. If you define a variable, it's immutable. And it's not shallow immutable, it's deep immutable. If you create a vector and it's not immutable, you cannot add things. It's immutable. If you want a variable to be mutable, you simply have to define that it's mutable. That is awesome. Believe me, that's really awesome. You have to be very explicit whether a variable should be mutable or not. That helps a lot in many cases, as all of you know who ever had a racing condition, for instance, or something like this. Yeah? This helps. Good. So we have the first method. Let's add the next method, and before we add the next method, I will add a little bit of code. I will not write this code, because I will screw it up horribly. I will tell you in a second what is going on here. And now let's start a little bit of code here. Let's say fn parse CSV line, and pass in a line which is a string, and we return a result of vec of string and parse error. AI is perfectly fine. Let's see if AI is capable of doing the rest for us. I would like to change that a little bit. So what I'm going to do is I'm going to create a struct which I call customer data. And this customer data contains an ID, a name, and a revenue. Take a look at the CSV, ID, name, revenue. I love AI. I love AI. It's so much simpler to change anything up. And here we can now return customer data. So this is how you create a struct in Rust. No, there are no classes. No, there is no inheritance. Nothing like this. You just have structs, full stop. That's it. Yes, it is object-oriented. Yes, there is a thing like polymorphism. Yes, there are vtables. And all these nice goodies come in with traits. Traits is the name for interfaces in Rust. So when you know interfaces from other programming languages, you know traits in Rust. Not. Because traits in Rust are so much more powerful than interfaces, and I would love to have 5 hours with you just talking about traits, but I only have 25 minutes, so you have to trust me. And if you are curious, take a look at traits after this talk, because they are amazing. So let's see if AI can do a little bit magic for us. Okay, that is good. That sounds good. So please do the rest. Yes, very good. Let's talk about this. Don't we all love AI? Yeah, let's talk about this code. Let's zoom in a little bit. That's a little bit too large. I think this is beautiful. Please take a look at this return type. This return type is a result. Result is a very, very, very special and important foundation of every Rust program. It's the return type that says, I might return a mistake, an error, but I also might return something useful. So what you essentially do, you say, green, this is what I'm going to return if everything is fine, everything is awesome, and this is what I'm going to return if something bad happened. And now let's take a look at what I have created here. This, ladies and gentlemen, is a dedicated type where you can read very explicitly all the different error conditions that can happen in this method parse CSV line. There can be a parse int error. There can be a parse decimal error. There can be an invalid number of fields error. So by looking at the method signature, the caller, the user of this method, knows exactly which error cases exist. You do not have to guess, add a try, catch everything, use a debugger, look what's thrown, and then hope that you catch all the possible exceptions that ever happen somewhere down the call stack. This is not the case here in Rust. If you want, you can be super, super explicit and simply say, you know what, these 3 error conditions can happen. There are a few special characters here which have special meaning. Give me a second, I will talk about that in a moment. Now let's take a look at this code. And the first line here is a thing of beauty. Why? You see, here in this case, I'm calling a method collect. Collect means take an iterator and create a data structure out of it. Do you want to have a vector, meaning an array list? No problem. Want to have a hash set? Let's get a hash set or a hash map or whatever you want. The point is, there is a single method collect, and the question which collect is called here. Am I collecting into a vector? Am I collecting into a hash set? Am I collecting into a linked list? Is defined by the data type on the left-hand side. Woo! That means that we have very, very special handling of method resolution. Here is where the magic of traits is happening. Let me show you something. This has nothing to do with our program, just so we understand what I mean. I can, for instance, say let numbers, and I simply say this is the numbers is a vector of something like this. This is perfectly fine, and I can define a vector something like this: 1, 2, 3, 4. Perfect. But now I can, on the left-hand side, remove this vector. See it here? It's still a vector. Yeah, no problem. It's a vector of I32. But now I can say numbers.push, and now I will add 42, and I will say unsigned 8, for instance. And see what's going to happen. Oh, I need to make it mutable. See what happened here. Do you see? Here, when I define the vector, that data type has not been fixed. It's still unclear. Is it a byte, 2 bytes, 4 bytes? If we take a look on the left-hand side, this was added by the IDE. It's not really standing here. We are still not saying anything about the data type. Hours later, lines later, we are pushing something into this vector, and only in this line here, the system understands what the data type of numbers will be. This is the kind of type inference that we are talking here. And the same is happening here. I always use collect, and the method which is really called is determined by the data type on the left-hand side. And it could be that this data type is not going to be fixed. Here the system says, I have no idea what you want from me. However, if I say fields.push and I push in a string, suddenly everything is nearly fine. No, in this case I need a type annotation. Sorry about that. But it's nearly fine. In many cases it would get it automatically. I don't have enough time to describe what I just did here. But trust me, it's really good. It works like a charm. Now here I'm just returning an error. And the next thing that I would like to point your attention to are these question marks. This is how you work with error handling in practice. What we essentially say with this question mark is we say, if an error happened, return error. If no error happened, continue. So you do not need to write the if. Anybody has ever written some Go code? Who loves error handling in Go? Do something if error, do something if error, do something if error. Do you know this kind of code? In Rust you simply say question mark. That's it. And the beauty here is that you can continue with additional functions here. Something, question mark. Some other thing, question mark. And so on. This syntax is perfectly fine. You can do that. And it's super helpful when it comes to iterators, for instance. So error handling works like a charm. Now, the thing is, this is an unsigned 32. This is a decimal, as you can see. Now take a look at the code that I've written here. Did I specify the data type here? Nope. Did I specify the data type here? Nope. Did I use a different method? Parse? Nope. If the compiler simply looks at these 3 lines, it has absolutely no idea what parse method I mean in line 43. And it has no idea what a parse method it means in line 45. But we are constructing a customer data down here. And here we are using ID and revenue, and it knows how customer data looks like. So it can have go back and say, okay, if this is the ID which is in customer data, then this must be U32. Therefore, this must be an ID of type U32. So this parse method should be something that has to do with U32. Got it? Isn't that beautiful? Isn't that nice? Can we take questions at the end? Is that fine for you? Yeah, I think somebody raised his hand. Okay, let's do it at the end. So you see, this works really nice. Now, in this case, a parse int error could happen. In this case, a parse decimal error could happen. How does the system know how to translate that into a generic parse error? The answer is this guy here, this guy, and this guy. This is the next takeaway that I would like to point out here. Macros. Yes, Rust runs on macros. Macros are everywhere. You have different types of macros. Macros are used all over the place. Everywhere. In most situations, you even have a macro on top of the main method. If you take a look at the main method by default, the single statement which is contained in a hello world function is a macro. Macros are super, super powerful. And don't worry, if you come from the C world and you are used to macros which are, I would say, search and replace on steroids, this is not the case here in Rust. In Rust, macros work on the level of the abstract syntax tree. So the compiler generates the abstract syntax tree, and you are essentially rewriting the abstract syntax tree. Some people created languages inside of Rust macros. There is a Rust macro to convert, what was the language? I forgot the language. Some strange language of the past into Rust just by doing a macro. You can really do whatever you want in these macros, and you can invent your own domain-specific language here and transfer it to something else. It works like a charm. Again, I would love to have hours to talk about macros with you, but you just have to trust me. And the whole logic that says, well, if this is an int parse error, then construct an instance of parse error and set the value of the parse error to a parse int error and inject the original error as a property on the new error object. All this code is generated automatically using macros. This is why macros are so important for Rust. Beautiful. So now we have learned a little bit about error handling. We have learned a little bit about method resolution. We have learned a little bit about type inference and other things. Now let me copy in a little bit of extra code. It's only just a few lines. Let's take a look at it. Here you see we have a struct, which is called parse file error. It's again an error object. But again, I would like to point out the hero of our story here, macros. We are using the so-called derive macro. The derive macro allows us to auto-implement certain behaviors or capabilities for our object. In this case, I would like to have the capability to print the content of this object on standard out for debugging purposes. Do you want to have the capability to compare two of these objects? Well, add equal and partial equal. Do you want to be able to clone such an object? Just write clone. Do you want to whatever? The derive macro is something that can generate, again, code for you because you are lazy. That's essentially the point. That's a good thing here. Don't get me wrong, not everything can be generated by macros, but a lot of things can be generated by macros, and you now should get an impression why these macros are important here. So the next thing that we are going to implement is we are going to implement parse CSV lines, content, which is a string. And in this case, we are going to return a result, which is a vector of customer data. And in error case, we are going to say that's a parse file error, something like this. I think that should be nearly correct. If I misspell this one, yeah, wonderful. Now let's implement this thing. Let's start with content. And this time, we are going to use iterators. Anybody programming C#, ling, MapReduce, heard before, Python list comprehensions, Rust iterators. They are awesome. They are really, really great. What we can do is we can say, hey, give me the lines. And this lines method here returns an iterator over all the lines. Then I can say, hey, skip the first one. I don't need one. Okay? Then we can say, enumerate, please. Enumerate means that I essentially get back not just the line, but also the index. Okay? You get the index and the line. Not that special. And then we are going to use a map here. Here you see how a lambda function, I will let AI finish the rest, and AI did a great job. This is how you write a lambda function in Rust. I am not capable of writing Ruby, but people told me that this looks like Ruby. I don't know if that's true or not. But essentially, you write these pipes here. In the middle, you have the parameters, and then you use the curly braces, and you write the implementation of the closure in this case. Okay? That is how you write a lambda function, or a closure, to be more specific. Here I'm just parsing the line, and then I'm using a specific function, which is a map error. And in this case, if there is any error in parsing this line, I am constructing an instance of this error object, and I'm extracting the index of the line where the error happened. See it? This is what I'm doing here. And then I can simply say collect. And take a look again at this thing of beauty. If we have 5 lines, and there is an error in the 4th line, then the system will run into this map error, create a parse file error. It will automatically recognize this map here, that this is now an error state. And it will return an error because this collect can handle the error condition and will correctly not return the vector, but will correctly return the parse file error situation that we have for this specific line. Try this feature, this example, in your favorite language, which is maybe up until this day not Rust. I mean, from now on it's Rust, I'm absolutely sure. But try it. Take this at home. I can give you the code if you want, and then compare the code. You will not be able to express it, very likely, in your language as consistent and clear and concise as here in Rust. I really love this stuff. Now good, that is good. Let's scroll up a little bit and let's call this thing. And please excuse the main method is really, really boring. So I'm going to copy in a little bit of code so that we have time for some last few things. Didn't I call it parse CSV line, something like this? No, I didn't call it like this. I called it, here I have an error. Okay, parse CSV lines. Now it should be better. Let's see. Okay, I don't see any mistake. What you see here is another cornerstone of the Rust programming language. I'm calling this parse CSV lines, and this is error handling as you typically do it in Rust. You simply say if everything is fine, go into the OK case. If there is an error, go into the error case. And here you see I'm printing out the error. Otherwise, I'm simply doing an iterator over the customers, extracting the revenue, calculating the sum, dividing it by the length of the collection and getting the average revenue. So you see, Rust doesn't need to be complicated. It looks like iterators in other programming languages. Rust can be sometimes a little bit complicated, but it doesn't need to be in many cases. Let's give it a try, okay? Cargo run. And then I have 3 minutes left. Yep, it works. You see, it was parsed, everything is fine. And just to prove that it really works, I'm going to throw in an error. Let's run it, and you see I get an error here in line 4. That's perfectly fine. Exactly what we wanted. Now, last little demo. Do I still have 5 minutes? That okay? Yeah? Perfect. 5 minutes, I'm done. Trust me. not a good thing to trust me on that. But well, I'll do my very best. I'll do my very best. I want to show you one single thing that is a trait. Let's implement a trait, and this trait is called has revenue. Or has revenue, something like this, and it contains a method, revenue, which returns the decimal, and I can simply implement that for customer data. Luckily, I have AI, so it will implement everything for me. This is a trait. It's a very simple trait. It's a trait which is just like an interface. Really nothing special. But now let me show you something. Impl has revenue for decimal. Isn't that crazy? I can implement my own trait for a system data type. Well, decimal is not a system data type. It's a data type of a different library. But I can add trait implementations to foreign types. I can even do so-called blank trait implementations, where I say all the objects which implement one trait now also implement another trait. So I can implement traits for a whole category of structures without the original author of this thing even knowing about me. In other languages, you reach similar things by doing structural subtyping, or as it's sometimes called, duck typing. If it walks like a duck, if it sounds like a duck, let's call it a duck. TypeScript has duck typing. Go has duck typing. In Rust, you have this powerful and much clearer system of traits that is way more powerful than what you have seen in other programming languages' interfaces. So I think I didn't overpromise. I only had 25 minutes. And I wanted to make as interesting as possible, as much code as possible. Luckily, nowadays, such talks are possible because we have AI, and AI saves you from watching me doing a lot of typing mistakes. I hope it was interesting. I hope it was a first impression what Rust is, and I hope you can now understand why I'm really, really a big fan of Rust, and I love writing Rust code. Thank you for having me. I'm open for any questions either now or afterwards, after the 3 talks. Thank you very much.
Thank you a lot. No? Yes. Thank you a lot, Rainer, for this amazing, not talk, but coding session. Are there any questions in the audience?
Yes.
Very top, okay.
The next question has to be here in the front, okay?
Please no.
Thank you for such a great talk.
Thank you.
Regarding the function, and then you already define what errors that will happen. So basically, or maybe this is just my, with my current knowledge, so you already predict what kind of errors that will happen in the function, but what happen if you are not preparing all of them? So for example, maybe you forgot that there's one kind of error that you haven't defined in the enumeration.
Yep.
What happened then?
Of course, this is possible. I was cheating a little bit. I am using a library here, which is called thiserror, which is very, very widely used. And you use this if you explicitly want to enumerate or list all the different error conditions. But there is an alternative library, which is called anyhow. I didn't have the time to make this demo. Anyhow is just with shrugging your shoulders. Okay, there was an error, anyhow. The only property that an object must have in order to play with anyhow is it must be convertible to a string. So you must be able to print it in a log. So if you write an application and you have a method, and if this method fails, the only thing that you're ever going to do is write the error in a log, then you can use anyhow. There is no point in being more specific. You can do what you say. I don't want to care anyhow. If there's an error, anyhow. I give you something which can be converted to a string. But this is not typically used in libraries where you have callers who really rely on what you create and who would like to maybe handle each different kind of error. In these situations, you are explicit. You have to think about your error conditions. You have to model your error conditions, and you use this error. Does this answer your question?
Yes.
Thank you.
Thank you.
Any other questions? Maybe one more, if you have one. Yes.
Thank you for the thank you for the presentation. I have a question about the supply chain security. Can you say a few words about that regarding the dependencies and also macros?
Yeah, of course. You have the dependencies here in the cargo toml file, and these dependencies point to a website which is called crates. Here you see it. And inside of crates, you have all the different crates. I'm now opening up the crate for a random number generator, which is very, very widely used. If you scroll down, you see it's really used, it's heavily used. I mean, the strange thing is you are using a random number generator and it's not even version 1. I mean, that is kind of strange for many people, but yeah, it is like it is. And the supply chain security is you have this cargo log file where you have checksums and so on, and these checksums are then checked against crates.io. Everything else is just like in many other situations. You have specific builds of the Rust compiler and specific crates which are on a higher level of quality for projects where lives depend on code, but this is not the area where I work with. In all my projects, only if I do a bug, it only costs money, but it doesn't cost lives. So I'm not the best person to talk to when it comes to really mission critical systems because I don't work in this area. So I cannot go into further details in building, I don't know, a control system for a hospital robot or something like this. Okay? Does this at least give you a little bit of an answer?
Yeah, partially.
Uh-huh.
And how is that with the macros? Are they included in the packages or?
Yeah, the macros are they are included in the packages. Exactly. I can show you one. I mean, if you want to see one, it's pretty simple. We can, for instance, go here in the print line macro. I can go here, and what you see essentially here is the system says print line macro. If it doesn't have any parameters, then we are simply printing \n. If it has arguments, to be more specific, multiple arguments, as you can see it here, then we are calling the print method and we are passing a list of all these arguments to the next macro, which you can see here. And now I could press F12 and I can go down into this next level of macros. And as you can see here, this is a macro of the standard library, but yes, the macros are part of the standard library. And the macros are executed at compile time. So you can do really crazy stuff with these macros. For instance, there is a crate where you can execute SQL statement against a relational database. And these macros, they run at compile time. So what they can do is they can connect to the database and check whether the SQL statement is preparable against the relational database so you do not have a typing mistake in the names of the columns in the database. You can do that. That's perfectly fine if you want. There is even much more. There are so-called const functions and so on, but I only had 25 minutes. I'm so sorry. But does this answer your question about macros?
Perfect.
Wonderful.
Thank you so much.
Wonderful.
Thank you for answering all the questions. For any more questions, I think Rainer will be here for a bit longer, so you can
Yeah, absolutely.
hit him up with all your questions while he's eating and drinking, and so are you, hopefully. And now let's continue with Max for the second talk about Rust in industry. Ja, willst du vielleicht durchs Heiden-Mikro nehmen?
Seems like we have a little bit more time. Are there any questions to Rainer while we're setting up the tech, as always?
How was the presentation software called you used? Which presentation software you mean? Cursor? I see. Is this really on? 1, 2, 1, 2. I'm using Sumit. I'm using the Windows subsystem for Linux to run Ubuntu on my machine, but my host operating system is Windows. So I'm using the Windows kernel and the Linux kernel at the same time. And under Windows, I use Sumit, which is a free software that you can download and simply run on your Windows machine. It doesn't run on any other platform, but for me it works perfectly fine because I love the combination of the Windows subsystem for Linux and Windows. That gives me the best of both worlds. I use Linux. I debug on Linux. I do all my development work on Linux. Everything is in Windows subsystem for Linux. That's it's a standard Win.
Why not Windows as a Linux as a host system?
Because of my business work, I am forced to use certain applications and drivers and so on, which are either very hard to get or not to get at all. In the last few years, I've tried multiple times to run my daily machine on Linux, and I always had so many troubles with some business applications that I'm forced to use when working with enterprise customers that I decided the combination of Windows and Windows subsystem for Linux is the sweet spot for me. My private machines, for instance, my laptop, which runs my 3D printer, runs fully on Linux. But for the business world, that works really, really well for me. Yep.
What made you get started using Rust? Like, when did you switch and why?
Oh, that's a funny story. The first language that not the first language. I do a lot of C# development, a lot of TypeScript development, and then I did a lot of cloud development. And in the cloud, you say container. If you say container, you say Go. And so I looked into Go many, many years ago. And I really liked Go, but I didn't like the syntax of Go. I mean, it's simple. I still do work with Go, but I don't enjoy writing Go code. And at one time, I saw that there is this technology coming up on the horizon, which is called WebAssembly. I am a big fan of WebAssembly. And when you say WebAssembly, you say Rust. And essentially, containers brought me to Go, and WebAssembly brought me to Rust. And I found out about Rust, I learned about Rust, and I immediately fell in love with Rust.
Is Rust, do you have always to fully compile the files to get it run, or is there also an interpreter where you can...
No, not an interpreter. You have to compile it. If you compile in debug, you have an incremental compile step, which is rather fast. If you do release builds, you always build from scratch on a CI/CD server, for instance. And let's put it that way, Rust isn't known to be pretty fast when it comes to compiling. We could also say it's horribly slow, because the Rust compiler is not directly spitting out machine language. The Rust compiler is spitting out LLVM, and then the LLVM toolchain is converting everything into machine code. And that simply takes a while, because Rust also doesn't have binary packages. So there are no DLLs as in .NET or jar files in Java. I'm not a Java developer. Maybe I'm saying something horribly wrong. So yeah, this is the answer. And I think you're ready. Yes. Good.
All right, test. 1, 2, 3.
Oh,
Nein.
right. My bad. Yes.
Test. Oh, okay, that sounds much better. All right. Well, thank you everybody for having me. Today can you see this? No? Perhaps? No, not yet. Hold up. Video settings. No?
Ja. Ja.
Okay.
Jetzt dürft ihr mal. Ja.
Yet. There we go. Okay. Let me start over. All right. Okay, thank you everybody. Now it works. Now you can see the fancy animations. My name is Max, and today I'm going to talk about Rust in the industry. I've been kindly invited and been approached by Matthias, so thank you very much for this opportunity. And let's dive right in, but first I'm going to yap about myself a little bit. So I'm Max. I work at Proxmox Server Solutions as a Rust and Linux developer. More Linux than Rust these days, but I still love Rust a lot. You can usually find me under the handle Equitosh online. I'm on Mastodon, but I'm not really that active, but you can stalk my GitHub if you'd like. I've been coding Rust for about 3 years, almost 2 years professionally now, and 1 year before that, mostly as a hobby and also at university, just a little bit, mostly trying to convince my lecturers to use Rust, because as soon as I discovered it, I was immediately passionate. I'm also the organizer of Rust Vienna, so if you're ever in Vienna, and we happen to have a meeting at the time, you can come over and you can listen to talks by our local community members. And currently I'm also trying to contribute to a library called Pi03, which is a library that allows you to very easily create native Python modules. So you write your Python module in Rust, and you can then use it in Python. So give me a show of hands. How many data science nerds are there? Oh, a couple, all right, decent. So you probably know Pandas, the library, right? There is also the cooler kid now called Polars, and Polars, for example, is implemented using Pi03. So I'm really happy to be contributing there. Non-commits haven't actually made it in yet, but I've got an open pull request and I got a whole couple milestones currently baking, but we'll see. All right. Oh, and I forgot to mention, I'm also a student at the University of Vienna. I study computer science. Still, unfortunately. But you all know that. All right, so let's start. Who actually cares about Rust in the industry? Well, I care. Otherwise, I wouldn't be. Otherwise, I wouldn't be here. I use Rust at my job daily, or almost daily, and the reason why I care about Rust is because it made me a much better developer in a very short amount of time, and it eliminates a huge amount of pain for me in my daily workflows, daily routines, whatever I'm coding. So the whole story sort of begins when I was writing a data structure for a course at university. So we have algorithms and data structures as a course. You probably do too if you're students. And one of the data structures you can code there, among some others, is a B+ tree. And because I had a really inflated ego, I decided to write the B+ tree, which it's the only data structure that comes with a disclaimer, and they will tell you, only choose this if you really like coding. And back then, I kind of had forgotten most of my C++ knowledge because I was mostly writing Python. So I didn't know how pointers worked, which is really bad if you're trying to implement a tree. I kind of forgot a lot of C++ specific semantics and syntax, which is also really bad if you're trying to write the hardest data structure. Nevertheless, to skip ahead a little bit, I managed to do it, but it was a huge amount of pain. And I didn't even get the best grade because I missed 2 deadlines. So it was as good. Had I just chosen a simple data structure, I would have gotten the same amount of points. So it's yeah. But anyway, during that time, I was using a lot of volgrind. If you've ever used volgrind, you know how painful that can be if you can't immediately spot an error. Especially in the tree-based data structure, it was, yeah, kind of painful. There isn't really any other way to put it. So I had to manually track down all of my allocations, and the allocations that I didn't free, and the allocations that I didn't make, and lots of other things like the null pointer segfaults and all of those good things that I got. And the reason why I care about Rust is because Rust doesn't allow you to make these errors. The Rust compiler will verify whether your program is actually sound, but more on that later. So who else cares? Not just me. Meta cares. You all know Meta, also known as Facebook, but not anymore. So they are recommending and encouraging Rust for performance-sensitive backend services, also C++. That is very surprising. Meta started making this recommendation in 2022. So a lot of their services in their backend are probably now implemented in Rust. They have tons of other programming languages too because they're huge, but it was quite a good, it was quite a positive surprise to see Meta actually recommend and encourage Rust and make it part of their supported languages. They also recommend Rust for CLI tools because Rust, through its very strong type system, is just perfect for doing data transformations. If you've got an input and an output that both are not really as dynamic and have defined structure, then Rust is just perfect. If you've got some kind of black box problem where you know this is what the input looks like, this is what the output should look like, Rust is perfect, which also makes it really good for AI and also for data science applications. For anything, really, except maybe a couple things, but obviously I'm here to shill Rust and not talk down on it. Now, who else cares? Google cares. They've actually conducted an internal study, and they've found out that, well, not a study, more a survey. They found out that 2/3 of respondents are confident in contributing to a Rust codebase within 2 months or less when learning Rust. That is very quick. Now, obviously, there's a huge disclaimer there because it's Google, and Google engineers are probably quite quick at learning new languages. But nevertheless, it's very nice and a very positive thing for Google to have published this in 2023. They also added that 1/3 of respondents said that they became as productive and as comfortable with Rust as they are with other languages in 2 months or less, which is quite fast, in fact. So when I started learning Rust about 3 years ago, it was a similar experience for me because I mostly had a Python background, and Rust kind of reminds you of Python a little bit here and there. So that was quite, yeah, I just had a nice learning experience. I think it took me like 3 months, plus minus a few weeks, mostly wrestling the borrow checker and some other things, but I just felt really comfortable with Rust very quickly, so that was very nice. All right. They also, Google also found that a lot of respondents were very happy with their code quality. So Rust, because as Rainer already mentioned, it doesn't have classes, it's not really as object-oriented. It does have objects, but you don't get to see them that often. Because Rust kind of limits its scope on what it can do and really emphasizes composition over inheritance because, well, you can't actually inherit anything. There is no inheritance. You kind of eliminate a lot of code complexity, which is nice. Because if there is something that I've learned in my time in the industry, that there is the greatest enemy is complexity. There are problems with a certain amount of complexity, and you usually cannot reduce this complexity. It's kind of like whether the problem is P or NP. Obviously, if you have the traveling salesman problem, you can't actually reduce it any further. Otherwise, we'd probably have a technological revolution at the moment. And the same kind of applies to certain problems that you have to solve when you're a developer. Other developers also know this. Some problems are just hard. And Rust makes it easy to deal with hard things because it forces you to break those problems down into manageable pieces. You can't write an abstract factory builder. Yes, I've actually written that for university course with Java because we had to. There is no such thing in Rust, which is very nice. And last but not least, they also say that more than half of respondents say that Rust code is incredibly easy to review, which is also nice if you're a maintainer of an open source library, for example. Your contributions are usually going to look, rather the syntax and semantics of your contributions are going to look relatively similar. There aren't going to be any hidden surprises. They're rather rare in Rust. Not that it doesn't have its sharp corners here and there, but it's just, once you learn Rust, there aren't really any new surprises, usually, from my experience. All right, there's another mention I want to do, and that's Discord. Discord actually switched their backend implementation from Go to Rust, specifically because they had to deal with the garbage collector. They The garbage collector was actually causing a noticeable lag spike in their API response time. And you could actually measure it. It was like in a very certain interval. So every couple, I don't know, within like a time frame or something, the garbage collector would actually cause a lag spike in the API. And in fact, when they transitioned to Rust, they found out that they didn't have to measure their API performance or response rate in milliseconds anymore, but rather in microseconds. So they became, on average, don't quote me on this, but they became faster by an order of magnitude, which is incredible. All right, that was a lot of shilling. Let's continue with the honorable mentions. Rust made it into the Linux kernel, where it's now being used to develop drivers and parts of the kernel that are still separate from the main kernel, but like drivers, they just need to interface with some C code. They don't touch any existing structures. Then there's also the Windows kernel, which is also kind of surprising. There is even a syscall that's now implemented in Rust in Windows, which also surprised me, but Microsoft is starting to rewrite a lot of their kernel infrastructure in Rust. Also Asahi Linux, which is a Linux distribution, maybe some of you might be familiar with it. It's basically a Linux distribution that allows you to run Linux on your Apple Silicon Mac, and it features a GPU driver for Apple Silicon, specifically written entirely in Rust. Then there is DNOW, you might have heard that, the better NPM. Typest, maybe you've not heard about that. That's an alternative to LaTeX that's written in Rust. It's quite popular, but it's mostly within the Rustation sphere. I haven't tried it myself yet. There's also Rust Python, a Python reimplementation in Rust. Gleam, a new distributed systems language based on the Erlang virtual machine. Then there is Rock, which is also a functional type of language, mostly for front-end stuff, interestingly enough. Then there is Sway. No, not the tiling window manager for Linux, but this is basically a language that allows you to write smart contracts very efficiently. I'm not in the crypto sphere. I just wanted to put it up there because it has a lot of stars on GitHub. And also SWC, which is a speedy web compiler. It's a JavaScript and TypeScript compiler that's, well, very fast. So I think you can see a theme there. It's usually about fast things. Anyway, all right, so I want to now talk about what problems does Rust actually solve. It solves quite a few, so you might already noticed. It guarantees memory safety without any garbage collection. It also guarantees null safety, so there are no null pointer exceptions or anything of that sort. It enables you to write concurrent code safely and quickly without having to think about race conditions and any other things. It's also very easy. This isn't something that Rust specifically solves, but Rust makes it also very easy to interoperate with other languages through its foreign function interface. And you can also easily support multiple platforms through code itself. So let's talk about memory safety without a garbage collector a little bit. So Rust references, as you've already seen in the previous talk, Rust basically allows you to have several immutable references with that &T syntax. So if you have a type T, the reference of T would be &T. And it only allows you one mutable reference, &mat T. So you can either, a lot of people can read, but only one person may read and write at the same time. So you can either have shared references or one mutable reference, and that is very, very important. Yes, this is also enforced by the Rust borrow checker at compile time, which is great. There are no runtime errors in that regard. Let me progress to some code. Here you have three functions. So one takes a shared reference, one takes a mutable reference and one takes ownership. So it moves the value into the function. So you pass on ownership of that value to the function, and now you don't own it anymore. These are quite trivial definitions, but they play a role in the next example, where we're just going to construct a vector. And then we're taking the vector via a shared reference. Well, that was simple enough. We can also take it via a mutable reference, but we have to specify that the vector is mutable first. So we cannot actually produce a mutable reference to a value that is immutable. We have to declare it as such. We can also pass on ownership. Now you see the absence of any references there. We are actually now passing on the value to this function. Okay, that's very trivial, very nice, very cool. But what happens if we try to, well, spoiler alert, compiler error, we can't actually generate a reference after we've transferred ownership. This is something Rust protects you against. Other languages, not so much if they aren't garbage collected. And of course, you can also, you can't actually create a mutable reference. Now, let me quickly change this example up. How does this play along with concurrency? So why do we say in Rust that we have fearless concurrency? So if we have a shared reference here, and we then spawn a thread, and we also give it a shared reference of our type, this is fine. The compiler allows it. Why? Because multiple threads can read the variable, because, well, we have a shared reference. So after that, we can also, we can give it a mutable reference here. Why? Because when takes shared up there finishes, we can produce a mutable reference. The thread doesn't start until the previous function finishes. But we can't create any references afterwards because the thread might still be running. So we can't create a shared reference while the value is borrowed in another thread. We also can't create a mutable reference, but I didn't put that on my slides. Whoops. All right. So let me see how much time I have, because I really have to get. Okay, there's enough time left. Now let me talk about null safety a little bit. This mostly revolves around the option trait. So since Rust doesn't have any segfaults or null pointer exceptions, or how Go, for example, calls them nil exceptions or nil pointer exceptions, I think. Rust solves this through the option enum that you've maybe already seen a little bit floating here and there in Rainer's talk beforehand. So it simply consists of two variants: the non-variant that doesn't have anything in there, and then sum, which takes a t, any t that you can think of, basically any type. You use this, since this is included in the standard library, it's automatically important whenever you write a Rust file. So you can simply create an option of a string, and then you can match on that option. So if our sum here is in fact sum, we can destructure it and then do something with the message that we've now extracted. Or if it's none, then we do something else. So this is called structural pattern matching in Rust. So this isn't the switch case statement that you might know from other languages. Java 21 kind of fakes it and also calls it pattern matching, but it really isn't. I think Kotlin does it. There are a couple others. Python now has it too. So structural pattern matching is really, 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 really powerful in Rust. And I wish I could talk more about it than on here, but unfortunately I don't have enough time. Then there is also this kind of syntax. So you can simply extract, you can simply match against one pattern with this if let sum kind of idiom, which is very convenient too. And now you might be thinking, okay, so it doesn't really, how does this solve null safety? So the thing is, in Rust, references can never be null. There can never be nothing behind the reference. So if you run this code in your main function, you will see that it doesn't actually panic. The assertion passes. That's because of an optimization that Rust does. So let me quickly go back here to the definition of option. You can see here that option has a so-called null variant, which is none. So since none represents nothing, and in fact, if the compiler knows it as, the compiler will basically enumerate it. It's called a tagged union. The enumerations in Rust are actually tagged unions, if you want to look it up. So for Rust, none just means 0, and some t means 1. Because there's already a zero present, the Rust compiler figures out, oh, references can never be null, but I have a 0 variant here, so I can just basically merge the two structures so they still have the same size, which is very useful, by the way, if you're interfacing with C, because there's also something called non-null pointers. So instead of having to check whether the pointer is null or none, you can create a non-null pointer, and that pointer will then guarantee that it's not null, hence the name. So if you have an option of a non-null pointer, you can, in fact, just pattern match on that pointer, and the compiler will tell you whether it's null or not, which is very, very nice. Now, let me skip ahead a little bit, okay? I'm starting to run out of time. Oops. Now, what does Rust do for interoperability for via its foreign function interface? So it's very easy to call functions from other libraries via Rust. You just basically say that a function is extern and that it comes from some kind of library. And then you can just call it. But the problem here is, or rather not problem, but the thing here is, you have to do it inside of an unsafe block, as you can see. Ooh, spooky. It's not as bad as you think. Unsafe just basically means, okay, I'm going to opt out of any guarantees that the Rust compiler gives me. So you just have to make sure that what you're doing is actually correct. So yeah, that's pretty much what unsafe means. And the great thing about unsafe is it limits the scope of where things can go wrong. So if your program suddenly behaves in a really weird and inconsistent manner, and you have undefined behavior somewhere, then you know it stems from an unsafe block. It's not like in, for example, C or C++, where it could be anywhere. It's specifically in an unsafe block, which really allows you to narrow down the scope of where things can go wrong, which is great. Then you can also call Rust from other programming languages, as long as they support the C API. You do that with defining an extern C in front of your function, and then you can just call that via C or C++ or any language. You also have to give it this no mangle tag up there. That's actually not a macro, that's a compiler intrinsic, or like a compiler tag. It basically just means keep this function's name as it is and don't convert it to your cool compiler internal unique identifiable name, so that you can just call the function from outside. You can pass data also over to anything that supports a C API. So if we have this struct here with user data, we give it some C-specific types that are also found in the Rust standard library. And then we have to make sure that the struct's layout is actually the same as in C. So we give it there's another tag here, the wrapper C tag. So this just basically means represent the struct like in C. So now the struct's layout is guaranteed to be the same as in C, and you can pass a pointer or a reference over to any C function, whatever you'd like. This is really important because otherwise, if you don't give it a tag, the Rust compiler will just say, yeah, this struct, yeah, I don't know if it actually exists after you've compiled your code, because Rust will generally very, very heavily optimize your code. Now, all right, supporting multiple platforms. I have to hurry up a little bit. Supporting multiple platforms in Rust is also really, really easy because it has a couple of macros that allow you to do that. So one of them is the config macro, the inline config macro. So for example, we're using config Unix. You can check whether you're running on a Unix or Nix-like platform. Or with config Windows, you can check whether you're running on Windows. which is really, really great. There's also a different version using this kind of tag, which is a bit more specific. But this tag basically only activates the expression below it, or that it, well, the expression that it tags, if the target OS value actually matches Android, for example, or iOS, or anything else. There are variables for the architecture, for CPU features, for operating systems, for so many other things, and those are all supported by the compiler. Excuse me, which is just great. So you can directly and at compile time verify whether your code will actually run on that platform. This is, even though it's just a little toy example, this is really, 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 really powerful. And I'm going to show you that in a second, actually. I'm going to do a little demonstration with the Bevy engine. Unfortunately, I was going to show you a really cool demo using my gamepad that I had with me, but it wouldn't connect with Bluetooth. We're not that ready yet. Technology isn't there yet, but you can run the examples of Bevy, the Bevy game engine, in your browser, and these are all written in Rust and compiled to WebAssembly. So everything you see here, unfortunately the loading bar here doesn't disappear, is written in Rust, runs on WebAssembly using WebGL2, or also WebGPU, or it will run on OpenGL on your Linux machine, or it will run on Vulkan on your Mac, or OpenGL on Windows, whatever you want, and it all does that through conditional compilation. So if you're a game developer, for example, or just want to write a graphics application, you can actually use that engine to ship your game or program to any platform, and you don't really need to care much about any extra steps or any invariants that you might have to uphold on that platform. So this is really, really cool. And now I'm going to hurry up because I'm running out of time. So I could go on about Rust now. I could go on about traits, structured typing, type state and type state analysis, asynchronous programming, and so many more things that Rust allows you to do, but unfortunately time is short. So thank you all for listening. I hope this was informative and has shown you why we actually care about Rust in the industry. It eliminates a huge amount of pain, and yeah, thank you very much. So I also want to mention my slides are open source and they're made with Motion Canvas, a TypeScript library. You can follow the QR code if you want to see them. I'm going to upload the rest later because I've made the last bits of my slides on the train. But you're welcome to take a look at them. Beware that the code is very procedural. But yeah, thank you.
Thank you so much for your wonderful presentation, Max. Are there any questions in the audience? There.
So thank you for your presentation, yeah. And I wanted to ask, because as we know, Android mainly relies on Java virtual machine. So basically compiling, if you want to run, for example, I ran C++ on Android, so I had to, I think it's called NDK, to basically compile the C++ for Android. So does it mean the Rust can also basically be compiled to a JVM bytecode?
To JVM bytecode, that is a good question. So the Rust compiler is based on LLVM. So technically, yes, I think, with an asterisk at the end. I'm not sure bytecode specifically, but I think you can embed it through different manners. If you're using Kotlin at the very least, I know that there's one project with an example where you can call Rust from Kotlin. With Java, you can probably use something like JNI too. For Android-specific things, I'm not really sure, unfortunately.
Okay, thank you.
Any other questions? Yes.
So you have said you're working at Proxmox. Do you? When I open my Proxmox interface, do I see something coded with Rust?
Not directly. Some things are coded in Rust, yes. My coworker actually cooked up a Perl to Rust bridge a while ago, so we are calling Rust from Perl. which if you know any Perl, you know how cursed it is, but it's really fun, and we're slowly transitioning from Perl to Rust. So yeah, there are a few bits and pieces here. We have a new experimental firewall that's actually completely written in Rust. There's a talk about it that you can look up on by the Linux Foundation. Actually, my coworker held a talk there recently. How he used Rust specifically to implement a new firewall, which is really, really great. So yeah, we're slowly getting there. It's just like with all other projects, actually fully transitioning to a new language will always take time, but Rust actually makes this really, really, really easy, simply because you can just, you can basically represent all of the conditions that your data has to uphold via types, called the type state pattern, look it up, which just makes it super easy to deal with anything that's going on in your code base. So yeah, that's where we're at right now. It's just like a lot of data modeling, a lot of interfacing, so yeah.
Nice, thank you.
Thank you again. And now we will go to Matthias, who will talk about Rust and security.
All right.
Let's see if technology works. Perfect. All right, I need a presenter. Perfect. All right, final talk. We already heard so much about Rust and like what makes it awesome. And I can just say I completely agree with everything that has been said. Like, if you should take one thing away from this event today, it's that you should really use Rust. Just forget about Python, JavaScript, Node.js, just use Rust. But with that out of the way, let's focus on security and find out, is Rust actually safer than other languages, and what makes it special? So a little bit about me. So I've been using Rust since 2020. And there I was really interested in like the low-level stuff like game hacking and like trying to get around anti-cheats. And there it's a lot about security. And before I was using C++ and I was really annoyed. I had a lot of issues. I spent so much time debugging. You won't even know. And I even have friends still today who are using C++ and they're spending a week on a heap corruption bug. And then they're saying to me, oh my god, the bug wasn't even in my code, it was in the damn standard library. And this is kind of prevented with Rust, just because there's so many protections in place. And yeah, I've been using Rust since 2020, and it's been awesome ever since. So what are we gonna look at today? First, we're gonna dive a little bit into the problem. Why is this such a big problem currently? Rust exists, why isn't this solved already? Then dive into some current solutions, examine why we need Rust, where Rust shines, some case studies looking at some companies, and then give a conclusion and see where we can go. So Microsoft released a really interesting statistic that ranges from, I think, 2008 until 2016, so 12 years. And they examined all the bugs and checked out which of those are actually memory safety vulnerabilities. And as it turns out, 70% of those are memory safety vulnerabilities. And as we've heard before, Rust is memory safe. So if we're using Rust, 70% of all the vulnerabilities are gone. But of course, Microsoft being Microsoft, they're investing a lot of time and effort into making C and C++ safer. But in a recent talk, they again showed a statistic. And as you can see, it's not really getting better. there's like some solutions that's getting now it's at like 65%, but it's still, that's a huge chunk. And if we look at another example, in Android, in fact, 90% of all the vulnerabilities are due to memory safety. And the biggest chunk is just out-of-bounds writes. Then there's also out-of-bounds reads, and there's many others which can't be prevented in some cases, like logic errors. But imagine you're using Rust, and suddenly 90% of all your vulnerabilities are gone. That sounds incredible. And it doesn't only happen to be with Microsoft and Android. Also, iOS has a similar issues where 60 to 70% of all the vulnerabilities are memory safety issues. And even all the exploited vulnerabilities, there was a study and it showed that 80% of the exploited vulnerabilities, that is journalists or very important people, politicians, they have been targeted by using memory safety issues, which is a big deal for our current society. And current solutions aren't perfect, as we saw before. A lot of mitigations exist to make it harder to exploit those issues. For example, ASLR to randomize where the program is put into address space. There's many others, data execution prevention, where you don't allow execution from unsigned memory. There's also control flow guards, shadow stack, you name it. There's a lot of research going on there because it's not financially feasible to rewrite all the C and C++ code. There's millions of lines of code. And there's also a lot of research going on with fuzzing and static analysis, but you have to be aware these are not foolproof. Very complicated bugs won't be found by using a fuzzer or just static analysis. So we truly need to get away from using memory unsafe languages to memory safe languages. Also, iOS and Android, they're using sandboxing. So there's certain operations that are really dangerous. Let's say a friend sends you an image and you need to parse that. You don't want to do that directly inside the kernel where all the passwords and all the sensitive data are. You want to do that in a separate process that has very few privileges. So even, in fact, if an attacker is able to exploit the image parsing, he'll just be in a sandbox. He won't have any privileges. But that's not quite perfect. We'll come to that in a second. And another solution, of course, is to just rewrite the code in Rust. Or, I won't say that too loud, but you can also rewrite in other languages, other memory-safe languages like Java, Kotlin, C#. But we're here for a Rust event, so let's stick with Rust. So I just want you to imagine, like, what would happen if these 60 to 90% of all the vulnerabilities would just disappear. First of all, companies, they would save so much money that could rather be spent on product development rather than triaging a bug, making sure you can reproduce it on your machine, than actually fixing it. A very complicated bug can't be fixed by a junior developer. It has to be fixed by a senior developer who really knows all the teeny tiny details that some expert is exploiting. And also for consumers, we want our software to be perfect. We don't want our image viewer suddenly to crash and not know, did we just get it exploited, or is just the software not as good? So overall, we can save a lot of issues and a lot of money, and it would just be nicer if we didn't have these bug class with memory safety issues. And now we come to Rust. As we heard before, Rust has memory safety without the garbage collector. And the without the garbage collector is really important. Because, as we heard, garbage collectors, they're slow. Nobody likes them. Wouldn't it be nice to like just deallocate the memory at the right time exactly when you don't need it anymore? Well, Rust can give this to you. And because of that, it's also really fast. It's using LLVM, it compiles to native code, it has so many optimizations. Your Rust code is even as fast, maybe even faster than a C or C++ code. And then we also have like a lot of zero-cost abstractions, so you can use things and safety mechanisms at compile time that aren't there at runtime. And since it's a very modern language, the ecosystem also is focusing a lot on just making it nice to program with, but also very safe. And this memory safety truly is by design. We already heard a bunch about ownership and borrowing, but there's also an initialization requirement. You have to declare the value of a variable before you can use it, which isn't a thing in C or C++. There's also lifetimes, bounds checking, null safety, thread safety. And if you look at all of those and check where are they actually enforced, compile time or runtime, it turns out all of these can be enforced at compile time, except bounds checking, we'll come to that. But this is truly what makes Rust so powerful. If you compile your code on your machine, you will know either it doesn't work because the compiler gives you an error, or it does work because it compiles. So let's look at an example. In this case, we have a variable called x, and we don't give it a value. In C or C++, this would compile fine. You'll just get some garbage memory from the stack or somewhere else, so you can read like arbitrary memory, which is a huge issue. In Rust, this won't compile. To fix this, so yeah, the compiler even has very nice compiler messages. Like if you've never seen Rust compiler messages, you should just know they're amazing. They even say what you should do. It says like at the bottom, add 42. So let's just follow the compiler. The compiler obviously seems to be right. Let's just do what he says, and now our program works. Then next, with ownership. We already heard a little bit about it. I will not just reiterate it, just so it really sticks. In Rust, every value can have one owner, and this ownership can be moved from a variable to a different variable. So if you look at the example at the bottom, first we declare a string s1, and we just name it hello. And then we create another variable called s2, and now ownership is moved from s1 to s2. And this means s1 suddenly doesn't exist anymore. This memory is undeclared. So if somebody tries to access it, he would write to undeclared memory, which is an issue. So if we use this example and we try to print s1, the compiler won't allow it, because the compiler knows s1 has been moved and doesn't exist anymore. So in order to fix this, we can either copy the value, so instead of moving it, we can use the clone function, then it exists in both places, or we can borrow it. And as we heard before, with borrowing, you can either have one mutable reference or any number of immutable references. In this case, we again have a variable called data, and we create two immutable references to that data, because any number of people can read from this variable. It won't change, so there won't be an issue. But if we try and do the same with mutable references, this doesn't work. Because imagine there are also threads involved. So what would happen if two threads try to write to the same variable at the same time? Do you now take the result of the first thread or the second thread, or do you try and merge it? Like, how is the merging operation suddenly? This is undefined behavior. In Rust, the compiler automatically finds this issue for you. In C and C++, well, good luck finding it. It's your issue. It's undefined behavior, it's defined, and you as a programmer have to deal with it. But you always have to keep it in mind. And in Rust, if the compiler says you have an issue, you probably have an issue. There are some bugs, but I would trust the compiler. And if the compiler says it's fine, in most cases, it truly is fine. And in order to fix this, you can just create a new scope. So you can only have one mutable reference at any given scope. So in this case, this again works fine. And now if you try and do immutable references with mutable references, again, this is undefined. You can have only one of those. Because what if somebody is writing and at the same time another thread is reading from that variable? So what if somebody writes world to the string now and is only halfway done, then suddenly the other thread that's reading gets like WOLLO, which, I mean, wallow is a nice word, but in this case it's not what we want. And again, the Rust compiler automatically finds this for you. Yeah, and in order to fix it, I just also want you to know the Rust compiler is really smart. There's a lot of smart people working on it just to make it nicer for you to program. And you don't even have to create a new scope. The compiler can automatically infer if there's immutable and mutable reference at the same time. Because in this case, the compiler automatically sees, hey, R1 and R2 aren't used afterwards, so it's totally fine to also have a mutable reference, which is really nice. And then there's also lifetimes. I won't go into too much detail because they're often very confusing for beginners. So even when writing Rust code, you often don't even have to worry about them. You can learn Rust without knowing about lifetimes. Just create a copy every time. Just ignore it in the beginning if it's confusing. But I still want to explain it a little bit. And lifetimes are used to ensure that references really are valid. So if you've been coding C++ or C, you can point to something. And if that something suddenly is moved to a different place or deallocated, then you have a pointer to nothing, which is a dangling pointer, which is something we don't want. So if we have an example like this, we first create a variable r at the top, and then we create a new scope. You can also imagine this, we're giving r to another function and it adds a value or something, and there we assign a reference to x. But x is dropped at the end of the inner curly brace. So x will be gone, but r is now pointing to it, which is not safe because if we're not printing r, I mean, it's also unsafe with printing because now we're printing memory that's not there anymore. It could be anything. It could be your password. We don't want that. So lifetimes work like this behind the scenes. R lives until the end of the main function because then it is dropped and deallocated. But x only lives inside the inner scope. So the lifetime is much shorter. And in Rust, for a function to compile, if you have a reference, the lifetime needs to be at least as long as for the variable that you have. So in this case, b needs to be at least as long as a. And in order to fix that, we can move x above r. And then if we create the lifetime, r will be allocated before x, so it will always be valid. And this is really nice because it's a very subtle behavior that often won't be caught even in a code review, but it truly has a big difference. And then also with bounce checks, so if you define an array in Rust, the compiler will automatically know if the index is defined, if it's in the array, because this array can't be modified, it's static. It will always have the size 5. So if you try and use index 10, for example, the compiler will already tell you, hey, this is probably an issue, you don't want to access array index 10. But if we're using a vector which can be modified at runtime, this won't happen at compile time anymore, because the compiler won't know, hey, maybe the user added something before he pushed 10 elements or removed 5. The compiler won't know. But the nice thing is, the Rust compiler already adds runtime checks to see, hey, is the size of the current vector, whatever that is that big enough for the index? And if we're still trying to access array index 10 and the vector is only 5 elements long, we get a panic. And this is similar to the unwrap and accept we saw before, which is a panic at runtime and just even says with a very nice error message, index out of bounds. And this was the index and this was the size. We also have null safety, as we heard before. I'll not go into details. We have the option type. And then to get the value, we can again use the match value. Or we can also use unwrap. And again, with the match, it's again, the compiler forces you, the programmer, to actually get the value and handle the error. And with the unwrap, you get an error at runtime. So in either cases, this is checked. There can never be null that you haven't checked. And in C or C++ or even Go, it's so easy to get lazy and just assume, hey, yeah, it's fine, I'll worry about it later, and then suddenly you're passing null around, and then you free functions deep, and you get an error there, but the error originated like in a completely different file, and it just makes debugging a lot slower and a lot harder than it should be. Yeah, and here again is the error that you get at runtime. And also thread safety, it's a really complicated topic. There's so many issues there. There's race conditions, deadlocks, bugs that can only happen in certain scenarios, which are the worst of them all, in my opinion. And yeah, let's look at an example. We already heard it a little bit before. We can create again a vector and add a few elements. And then we can create a new thread, which will add an element, and also in the main thread, also add an element. So you should imagine when you call thread.spawn, then there's a branch. Now you're executing in the main thread, but also in the separate thread. And here it's, I mean, I could imagine this would work in another language. It's not an issue. Then if you execute the main thread first, then the order is 1, 2, 5, 4, or if the new thread executes first, it's 1, 2, 3, 4, 5. It's not a big deal. But what if we change this example, and instead of pushing an element in a main thread, what if we drop the vector? Suddenly the memory is gone. How does the helper thread know that the memory is gone? And the Rust compiler automatically finds this and enforces that you can't access memory at the same time, so that you have a race condition, and also that the memory can't be gone. In this case, to fix this, you either have to use the ownership concept from before again. You can move the data from a main thread to the thread, and now the thread owns it. As we heard before, single owner. And oh, okay, interesting. I won't go into any more details. It's a really complicated topic. If you're interested, I highly recommend checking out the Rust book. Okay, there we go. And yeah, the Rust book generally is like a great resource to learn Rust and get started. It takes you from the very beginning to really advanced concepts. And there they also talk about message parsing, how to handle a shared state using a mutex and reference counters. There we go. Okay, now enough about all the features that Rust has. I'm sure you all now know how amazing Rust is. Let's look at some companies that are actually using Rust in production, not just for the performance or nice usability, but actually for the security. And one of them is Microsoft. They have a library for font parsing, and as you might imagine, font parsing is quite scary. There's so many different languages: English, German, Hebrew, Chinese. Like, how do you handle all of that? So it's not only like handling the font and like maybe parsing it, it's also how to render it and like arrange it on display, which is really a big issue. And also, this library should be cross-platform because Office exists on many platforms. There's even an Android app now for it. So Microsoft also wants the code to be portable to different platforms, which with C++ or C can also be an issue. And font parsing in general, huge amount of complexity, so huge potential for logic errors and bugs in general. And what Microsoft did, in 2020, they took 2 engineers for 6 months and rewrote it entirely in Rust. And what they saw is not only that memory safety was now much better, the performance even improved from 5 to 15%. Of course, we can't give Rust all the credit. This could also simply be due to the rewrite, but it's still very nice to have a performance improvement. And another case study that's really interesting is Android. A lot of you probably have Android devices, and Android is using mostly Java and Kotlin on the surface, but there's also lots of C and C++ down below in the lower levels. And this C or C++ can be run in a sandbox, as I hinted before, for example, for image parsing. But sandboxes aren't perfect. Imagine you have a really old phone with Android, I don't know, 15. That's going to be really slow because sandboxes are very resource intensive. And sandboxes also aren't perfect. You can't just throw a sandbox on everything because attackers can still use chained vulnerabilities to escape the sandbox and then maybe access the kernel. So the Android team did something really smart. They looked at all the vulnerabilities and checked whether is it an old code or actually new code. And as it turns out, there kind of is an exponential decay for bugs in code. So if we look here at the code that's 5 years or older, this code rarely has bugs. And intuitively, this makes sense because this bug has been analyzed so many times and all the vulnerabilities already have been fixed. And the new code has the most amount of vulnerabilities because less people have looked at it and actually checked if it's safe. And this also in turn means you actually shouldn't rewrite all of the old code bases that are in C or C++ in Rust. You should rather focus your efforts on rewriting all the new code in Rust, because then you get rid of this huge chunk. And then later, if you have time, you can still rewrite the rest in Rust. And this approach is generally, so Android is also generally shifting from prevention by using mitigations or making C or C++ safer, more to actually preventing this bug in general by using memory-safe languages like Rust, Java, or Kotlin. And they've been doing this since 2019, which is Android 10. And across the years for Android 11, 12, and 13, you can see that the amount of memory safety issues have gone down year by year. Of course, this could be due to many factors. Maybe less people looked at the code and less people found bugs. Maybe the engineers just got better and are writing more safer code. But if you now plot the amount of memory safety issues with the amount of memory unsafe code that's written, you can clearly see a correlation. If you write less unsafe code, memory unsafe code, there's also suddenly fewer memory safety issues. Of course, this is a correlation. This does not mean causation, but it's a first step into the right direction, in my opinion. And in Android 13, already 21% of all the new code that has been written has been written with Rust. And this is already 1.5 million lines of code, which is so much. And some of those components that have been written are the ultra-wideband stack, DNS over HTTP3. There's also a Bluetooth implementation in Rust, which is not yet in production, but hopefully soon. And in a blog post from 2022 that outlined these results, they also mentioned 0 memory safety vulnerabilities have been found in Rust. Of course, this number probably isn't gonna stay 0 forever, but it's still a massive improvement compared to C or C++, which, are much worse in that regard. And I just want to highlight one part from their blog post, which says, this safety is achieved while providing equivalent performance to C and C++. And this is really the important part. Nobody's going to use a language that is slower and has better security. I'm sure you can use Java or Kotlin, but because Rust has the same or sometimes even better performance, it's an ideal candidate to write new code in Rust rather than C or C++. And there's also many other companies that are using Rust. We already heard in the previous talk, there's also Firefox with the browser engine, there's Huawei, who's also using it for the operating system, Amazon for the cloud hypervisor, there's Cloudflare, Dropbox, and you name it. There's so many more, it's only increasing every day. And I just want to highlight in a conclusion that Rust truly is the perfect match between safety but also performance. And the recommendations from before are just write new code in Rust rather than C or C++. You'll get rid of 70, maybe even 90% of all the memory safety issues. Of course, there's still potential to make mistakes. And for really critical components, like in the Windows kernel for font parsing, which has had issues in the past, it really makes sense to use Rust and also to rewrite those components. And with that, I want to thank you for your time, and I'm open to answer any questions. Afterwards, there'll be food and drinks. I'll also be there. Yeah, thank you. Any questions? All right, one here.
Where do you use currently Rust? Personally.
I mean, personally, it's like I've done a lot of Windows development as well, and I even got started with Rust because I wanted to write a kernel driver on Windows. And back then, this was very undocumented. I had to struggle a lot, and yeah, like just for really low-level stuff. And maybe to add to that story with Windows kernel drivers, it's really nice because the industry now is putting so much money and effort into really getting Rust to those systems. 4 years ago, Windows didn't even acknowledge Rust publicly. And I had to figure out myself how to get a kernel driver written with Rust to run. And now, last year, Microsoft even added their own bindings for Windows kernel drivers. And now Windows kernel drivers are officially supported with Rust, which is really amazing. And you just get to see how much the industry needs a language like Rust. Any other questions? Yeah.
Thanks. Okay, I have a question about the compilation and obfuscation. Is it still easy to decompile it and get source code?
So Rust is a compiled language. So there's LLVM, which compiles your Rust code to assembly. So I would say it's already much harder for someone to look at. But of course, there's still skilled people who can decompile this code. And Rust has some different behaviors. It's compiled differently to C or C++. But I would say it's still possible, and there's entire products that are sold just to make it harder to analyze. And personally, I've looked at Rust code, decompiled it a bunch of times, and async Rust really is much more complicated to analyze because it's using a state machine. So now suddenly you have to reconstruct a state machine in your head to try and figure out where the code is jumping. But to come back to your question, yes, it's possible to decompile Rust code. It's different, but still possible. Does it answer your question?
So you've mentioned a bunch of times about the concurrency and mutual exclusions. And the first question would be, for example, in many languages like Java, there are like real threads which use, I think it's fork syscall, and there are like pseudo threads. Like I think it's called goroutine in Go. And how is it implemented in Rust?
So the std thread that you saw before, that's really a real thread. And Go has like green threads or light threads, as I call it, I think. And those don't really exist in Rust. But when you're using async Rust, you have Tokyo, for example, an async scheduler, and that in the background has like a thread pool of like 16 threads if your CPU has 16 threads. And then it takes the async code and puts it to whatever thread currently isn't doing anything. And that kind of emulates like the green threads or lightweight threads. Yeah, does it answer your question?
Yes, because I've seen a bunch of, benchmarks where like Tokyo threads are actually perform much better than native ones. So I was wondering how it works, but yes.
Yeah, it's always a trade-off of like how much like overhead is there due to the communication of like a thread pool, and like yeah, it's always a trade-off. You have to look at it. Yeah, I would say to not keep you guys waiting much longer. The food outside is already waiting for you, the drinks as well. I would just close the Q&A for now. thank you so much for being here. I was also part of organizing this event, so it's like really amazing to see so many of you here. The speakers are still here for drink and snacks, so you can talk to them if you have any more questions. And without further ado, let's just end this event, grab some drinks and snacks, and thanks for being here. Thank you.